Hello, my name is David Hawkins, and today we're going to be talking about my Flyball Tachometer project. This was for my mechanical measurements class in my undergraduate of mechanical engineering in the University of Cal Poly Pomona. So let's get on with this, shall we? All right. So introduction slash theory. A flyball tachometer is a device used to determine the rotational speed of a shaft. And that shaft might be coupled to an engine or to an electric motor. As the shaft rotates, a centripetal force is created on the weighted flyballs, as you can see on the right, which displaces them upward and outward, causing the sleeve to translate upward or downward. And this translation could be used for other mechanical systems or for the system that it's coupled to. Such as an engine or a throttle. The displacement of the sleeve can be calibrated slash calculated to measure the speed of the shaft. Um, of course, depending on what your project is. In this project, we did both. We calibrated it, but we also calculated it so then we could compare. Okay, well, the project design requirements were to design a sensor to determine the speed of a shaft or a motor. And we were to use an LCD screen and mechanical indicator to display the speed of the shaft. Um, a flowchart of our system and our project. We have a potentiometer input into our Arduino, and that controls our motor, which is connected to our shaft with the flyball. And a sonic sensor is monitoring the bottom plate of that flyball system and it is being read by the Arduino, which converts it into signals for the LCD screen to determine the speed and the height of the flyball. We also have a mechanical indicator, which just basically directly takes the height of that bottom plate of the flyball and turns it into a measurement, as you'll see soon. Our mechanical design, of course, we had flyballs weighed down by metal. These containers, as you can see in the red, are nuts and bolts. They have nuts and bolts in them. Um, we have a motor, Arduino, motor driver, ultrasonic sensor, which were all utilized from a previous project. The main structure of the flyball system was FDM 3D printed. The metal shaft and compression spring were bought separately and off of McMaster-Carr, and the indicator arm moves with the bottom plate. The bottom left, you can see the the movement between two different speeds. As you can see, 0 to 70 RPM, because that's about that range is before it breaks the friction between the shaft and the bottom plate. And then at 400, which is roughly the maximum speed that we'll be operating this flyball at. And you can see how it goes outward and upward. Okay, mechanical design continued. What I have here listed is just main components of our system, or at least a mechanical system. We have pillow block bearings, which are um, attached to the back plate of our system, and the back plate is made of regular plywood. We have a step down pulley from the motor to that main shaft, and we have the indicator arm on the left. We have the weight containers. We have the linkage, shaft collar, and spring slash shaft. As for more detail on the mechanical indicator is connected underneath the sleeve of the flyball tachometer. Um, as you can see on the bottom right, it's held in by an interference fit. Um, the bottom plate and the indicator arm are coupled, at least in the motion along the shaft, but they are not coupled. The indicator arm is not coupled to the shaft, as is the bottom plate is. Um, and that bearing basically allows the rotation of that indicator arm, um, but not for it to be coupled. The height of the arm, the height of the arm was labeled according to the shaft speed. As for analysis, we created a force body diagram, as you can see on the left. The spring force, the centripetal force, and the weight were accounted for. In the middle, you could see um, our conversion from kind of like those forces into more of a system of equations, um, dynamics and statics. And on the right, you could see the kind of the formulation of our matrices, the A and B vectors. And basically, we just inputted it into MATLAB and we solved for three different changing variables, the change in K, which is the spring constant rate, the change in the speed, which changes the force of the centripetal motion, and also the weight, which we input into the container. As for MATLAB analysis, we start from the right. We have three different changing variables, the weight, the RPM, and the spring rate. And then we decided that we would lock in one variable, which would be the spring, purchase the spring. So then it turns our 3D plot into a 2D plot. So then now we have a changing weight and the RPM that it's able to reach from completely bottoming out that spring. And we decided to play a little safe, not to go up into a lot higher RPMs because um, due to safety concerns of our material of choice. So then we decided a zero point 0.5 newtons of weight on either side of the of each container of our fly ball. So then from there, we locked that in, then we got to the left plot, and then we were able to determine the change in the height that it would raise depending on the RPM input into the shaft. Um, and this curve is a theoretical plot. System parameters from all that analysis, our max shaft speed will be 450 RPM, max motor speed about 1350 RPM, so it's about a 3-to-1 ratio from motor speed to shaft input. Max plate displacement will be roughly 33.5 millimeters. The added weight on either side will be 0.5 newtons, and our spring rate is roughly 412 newtons per meter or 3.25 pounds per inch. Some stress analysis was performed in SOLIDWORKS simulation. Uh, we we had the system undergo a centrifugal force at 450 RPM, um, and it indicated, as you can see, at least from the color indication, that we're reasonably below yield of our material, so it's comfortable to operate at the 450 RPM range. Okay, so for electrical design, our system utilizes Arduino Uno R4 ultrasonic sensor, IBT2 motor controller, and 120 volt AC to 22 volt DC power supply. On the right, you can see a relatively crude uh, electrical diagram, but one that was able for us to move forward with. Um, at least for more of a rundown of how it's working, our potentiometer voltage is being measured by the Arduino, and that Arduino remaps that voltage range into a PWM signal for the motor controller. So when the potentiometer voltage is 0, the motor controller is outputting a voltage for the motor to be 0. And then when the potentiometer voltage is at peak, the PWM signal for the motor controller to the motor is 450 RPM. And from there, the Arduino outputs all that data on the LED display to output the RPM and the ultrasonic distance. All right. For electrical wiring, as you can see on the left, my hand's controlling the potentiometer, which is then controlling the system. We're outputting a distance of the ultrasonic sensor, and we're also outputting in RPM. On the right, just more labeling of the components, potentiometer, OLED display, IBT2 motor controller, and on the very right, the power supply. And of course, we're utilizing a breadboard system for rapid prototyping. For calibration, um, For the ultrasonic sensor, we calibrated with a caliper, and we tracked what the distance the ultrasonic sensor was reading, but also we were tracking or measuring the distance from from the bottom of the or the very edge of the ultrasonic sensor to the edge of the indicator, or actually edge of the bottom plate, and then we were comparing the two. I will move my little video screen. And as you can see in the top right, we have the caliper distance versus the ultrasonic sensor distance. So then when the Arduino is reading that sensor distance, we can recalibrate it into this equation for a more reasonable and accurate caliper distance, which we will use for when we convert the distance to RPM, and we calibrated um, that by using a handheld tachometer and a little uh, reflective strip at the very top bracket. And we read from the Arduino what the height reading was and what RPM it was from the handheld tachometer. As you can see, we formulated this long equation, which was then inputted back into the Arduino for a more reasonable and accurate RPM range. I will now play a video of the operation in my garage. As you can see, the top is the height, the bottom is the RPM. Mechanical indicator was reading that same, relatively the same RPM. Again, if I did not mention this, this was calibrated by um, by marking out the different RPMs as the height of the mechanical arm was raised as we increased the speed. This video is comparing the display, the mechanical indicator, and also the tachometer for a relatively reasonable accuracy between all three of them. Each component was tracked for the shipping, the cost, and the quantities. We determined that the collective value was around $210. Um, the total input cost for this project was $79. Um, was the cost if we were to buy each component at the very beginning of the project, but since we utilized a lot of the components from previous projects, we had a very low input cost, below the $100 requirement for this project. Because we only had about a month to complete this project, so we generated a Gantt chart to keep us on track. Some of our tasks included the initial design, the CAD modeling, the printing, the electrical networking or electrical assembly, creating the presentation, creating the YouTube video, and the final testing. The project was completed on schedule and, of course, successful calibration and testing of our machine. All right. So for continued work and potential improvements of this project, acoustic analysis would be beneficial to perform. So we can visualize more of how the wave performs and bounces off the surfaces for the ultrasonic sensor to gain more accuracy from that sensor. We can also perform vibration/stress analysis on the linkages in the whole system for that matter at increased speeds. So then we can see how it performs and get more of a full range of the motor because our motor can operate at 10,000 RPMs at around 22 volts. So it'd be for fun, we could operate it at the max speed, but of course that downstep ratio from the pulley would output a 3000 or roughly 4500 RPM to that shaft in Flyball. So performing vibration/stress analysis would help us determine if there's possibly a natural frequency and if our linkages can handle the stress of the centripetal force that is being inflicted on it at that speed. And of course, to get higher speeds and manage that full compression of that spring, we can increase the spring rate, or we can decrease the weight that's inputted into those containers. And from there, we can reprint linkages with a stiffer material or a changed geometry depending on how that system performs under stress and if we need a stronger material or stronger linkage. Hey guys, so this is the end of this video. I hope you enjoyed it as I did. It was very, very fun. My end of semester, end of undergraduate project. Not my senior project, but it was very fun to work with my teammates to apply the foundational knowledge to this project, learn about flyball systems, flyball tachometers. I had no idea how they worked, but I did some research and this is kind of the output of it. And we're lucky that we had other parts on hand to build off of. And also that McMaster car was so close in Norwalk in Southern California. But it's just very fun to simulate and kind of formulate equations and code and work with Arduino again. Been working with it for a while, and hopefully it can translate to other projects and perhaps in my engineering career. So I thank you guys. Thanks for looking and staying and viewing and doing what you do best, you know. Okay, goodbye.